Hi, welcome back. So today's lecture is on carbohydrates. Okay, so before we start carbohydrates, let's recap a little bit on the stereochemistry. So in stereochemistry, we learned two different naming systems for chiral molecules. Okay, so the two naming systems are one, plus and minus. So plus and minus is based on optical rotation. So it's based on optical rotation, and then R and S is based on the position of bonds in the chiral carbon. So these are two different naming systems. So for carbohydrates, right, there are more naming systems. And at least I think about at least two naming systems for carbohydrates. So the tricky thing about this is that the naming systems for chiral molecules, right, will apply to carbohydrates, because carbohydrates are also chiral molecules. They have a lot of stereocenters, so they also apply. So the tricky part here is to distinguish between the different naming systems and not to not to mix up the thing, especially some of them they use the same letters. Okay, so without further ado, carbohydrates. Okay, so carbohydrates have this formula of CnH2ON. That means carbon bonded to H2O. So more carbon and means more H2O. So this is actually the reaction that happens in leaves. So carbohydrate, the words carbohydrate actually comes from the word carbon and hydrate. So they shorten it to carbohydrates. So in biochemistry, carbohydrates are also called saccharides. So the word saccharide comes from the Greek word saccharon, which means sugar. Okay, so carbohydrates are a major source of metabolic energy, both for plants as well as animals. So animals in general depend on plants for food, because most of the energy on earth actually comes from the sun. So aside from the nutritional value of sugars and starches, they also have a different function. So some carbohydrates actually serve as a structural material. So the most common being cellulose. Cellulose gives plant wall is structure, but also there's also lignin. There's also lignin and also chitin. So there are also similar carbohydrate types of molecules. So a component of and also some of these carbohydrates are also used in energy transport, such as ATP. And of course ATP is also a nucleotide, which is an essential component of DNA and RNA. So saccharides are subdivided into four different groups based on the size. So monosaccharide is the simplest form. It is composed of one sugar unit. So one sugar unit is a monosaccharide. When you have two sugar units bonded together, right, then it's a disaccharide. And when you have 3 to 10 sugar units, it's a oligosaccharide. And when over 10 sugar units, it's considered a polysaccharide. So the reason why I classify based on size like this, right, is that the size will affect its properties by quite a lot. So in general, for sugars to be able to generate energy, right, most often you have to hydrolyze it into a monosaccharide form, where it is quite often converted into glucose in the body. So when it's converted to glucose, then it's actually easy to produce energy from it. So in general, most of this eventually will be degraded to monosaccharide, but the size of it affects its properties a lot. So like, especially for oligosaccharide and polysaccharides, so the two of this, it's actually very similar because they are both fairly large molecules, oligo and polysaccharides. But the main difference between oligo and polysaccharides is that oligosaccharides are usually a lot more water soluble. Polysaccharides is a lot more difficult to dissolve. Even if you take a soluble polysaccharide like starch, it's a lot more difficult to dissolve starch compared to a small oligosaccharide. Okay, so in general, sugars are considered monosaccharide and disaccharides. So they're commonly referred to as sugars, and they are quite often sweet, but not always. So whether it's sweet or not actually depends on the shape. So naming of sugars will always have the suffix "-ose". So that's why blood sugar is glucose, table sugar is sucrose, milk sugar is lactose. And lactose is not really sweet, but it still has the suffix "-ose". Okay, and you can also group the monosaccharides into different groups. can be aldose or a ketose. So if your monosaccharide has a aldehyde group, it's a aldose. If it has a ketone group, it's a ketose. And also, depending on the number of carbons, right, you can also classify it by size. So it can be a triose for 3 carbons, tetrose for 4 carbons, pentose for 5 carbons, hexose 6 carbons, heptose 7 carbons, and octose 8 carbons. You can classify that. So glucose is a aldohexose. So glucose is a aldohexose. Okay, and sugars are often assigned according to D and L nomenclature. So this, you notice this one is a big D and big L, right? It's different from the small d and small l. Small d and small l is actually the same as plus and minus. So this is big D and big L. So it's a different naming system from plus and minus, and a different naming system from the R and S. So this is a different naming system, and D and L naming is based on the penultimate carbon. So penultimate carbon is a chiral carbon, but not just any chiral carbon. It is the chiral carbon or asymmetric carbon which is furthest from the carbonyl group. So carbohydrates will always have a carbonyl group. So the chiral carbon that's the furthest away from the carbonyl group, right, is the penultimate carbon. So you must be able to identify which is the penultimate carbon before you can do a D and L assignment. And another thing that you require for D and L assignment, right, is you need to draw a correct Fisher projection for the sugar. So it's based on the Fisher projection. So for the penultimate carbon, right, on the Fisher projection, if it's on the right, if the OH group is on the right, it's a D sugar. If the hydroxyl group is on the left, it's a L sugar. So it's named based on the penultimate carbon and also the Fisher projection. Okay, so you can see here, this is the Fisher projection, this is the Fisher projection. Okay, and remember when I said in stereochemistry, right, if you fix the position of one of the functional groups, right, one of the substituent groups, right, there is only one correct drawing. So in the case of carbohydrates, right, this is what Fisher fixed it, because Emil Fisher worked on carbohydrates. So he fixed it in such a way that when you draw Fisher projection of carbohydrates, right, you must draw the carbonyl group at the top. That means as high as possible. If this is a ketose, right, you draw it as high as possible. If it's an aldose, it must be on the top. If it's an aldose, it must be on top. So the ketone or the aldehyde group is always on top. So this is the rule set by Emil Fisher. So this is actually to standardize drawing so that for each sugar, right, there is only one correct Fisher projection drawing. So it's a very, very fixed drawing. There's no flexibility in, because you already fixed one group, right, there's only one correct drawing. Okay, so this is the carbonyl group. This is chiral, 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 not chiral. So this is the penultimate carbon. And because this is the penultimate carbon, right, the OH this one is on the right, so it's a D fructose. This one is on the left, so it's a L fructose. And D fructose is minus, is level rotatory. So this is to show that the D and L here, right, is a different naming system completely compared to plus and minus, R and S. So different naming system means they don't influence one another. They are totally separate naming systems. And Fisher projection, how you draw this is important, because if you draw the projection, if you draw the carbonyl group at the bottom, right, would you still be able to do a D and L assignment or not? The answer is no. So Emil Fisher created these rules based on his Fisher projection, and the rule also states that the carbonyl must be on top. If you draw it the other way around, right, the D and L assignment will not be correct. So this is why the Fisher projection is somewhat rigid. Okay, and in many cases, the monosaccharides will usually form a ring. So it's usually in equilibrium between the open chain and the cyclic hemiacetal form, or the ring form. So they'll automatically form a hemiacetal. In fact, in a solution, right, open chain form is present only in very, very small amounts. It's there, we know it's there, but usually we can't really detect it much because it's very small amount. So most of the sugar will actually be in the hemiacetal ring form. So that's why most of the time when you see sugars, right, it's usually drawn as a ring. And sugars can be in the furanose or pyranose form, because this is the 5 and 6-membered ring form. So these two are stable. And the furanose and pyranose is named after the compound furan and pyran. So furan and pyran are not sugars, but they have a ring structure that's similar to sugar, and they have the oxygen in the ring. So that's why they call it a furanose and pyranose, because it's somewhat similar to furan and pyran. Okay, and to draw chiral projections, to draw chiral structures on rings. So Fischer projection is very good for drawing many chiral centers in a linear molecule. Okay, but for a ring, right, we cannot use Fischer projection. So for a ring molecule, you use the Haworth projection. So Haworth projection is to draw chiral carbons in a ring. So it's mainly to look at chiral carbons. So Haworth projection will not be representative of the true shape. That means it will not match the shape. If you want to draw the matching the shape, right, it's better drawn using a chair diagram. So you can see the different sort of drawing, right, is designed for different purpose. So Fischer is for linear chiral molecules. Haworth projection is for cyclic chiral molecules. Okay, and how you draw Haworth projection, basically it is a ring this way, drawn this way. And for the bonds, right, you notice here, it's not drawn according to the shape, it's just drawn as a straight line like this. So the Haworth projection is drawn as a straight line. So this allows you to see which is on top, which is at the bottom very easily. That's why the Haworth projection is good for this purpose. Okay, so how would you convert this into this and into this? Okay, so first you have to draw it with the carbonyl group right at the end. So one rule is this one must be right at the right, extreme right. So the rule for drawing a Haworth projection of sugar, right, is the carbonyl group, which here becomes the OH group, right, must be drawn on extreme right, and the O oxygen must be at the back. So the ring oxygen must be at the back. Okay, so one important thing here is that this is not a chiral carbon, but after it forms a ring structure, right, it forms a hydroxyl group. So this is a chiral carbon, so it creates a new stereocenter. This is another stereocenter. And notice double-sided arrows, right? That means hemiacetals are in equilibrium with the open chain form. That means this can change into this. It is in equilibrium because this structure here is not very stable. So it does change. The bond will break and then it will form this. Okay, so alpha glucose means that the OH is at the bottom of the ring. Beta glucose means the OH is on top of the ring. So certain rules will apply, like the O must be here, this one is the extreme right. And because this is a D sugar, right, the CH2, the extra non-chiral carbon, right, must be on top, because this is a D glucose. So this is how you get alpha and beta glucose. So you must draw the structure first. So glucose is an aldohexose that's usually in the pyranose form, but it can adopt a furanose form. So it depends on what enzymes are reacting with the glucose. So the anomeric carbon is usually drawn at the extreme right. The ring oxygen is drawn position away from the viewers. And you have two possible hemiacetals, alpha and beta. Alpha if the OH is below, beta if the OH is on top. So glucose can be a furanose depending on what sort of enzymes that force it into a certain ring form. But usually it is in the pyranose. In fact, most sugars are usually in pyranose unless there's something that forces it into a furanose form, because pyranose is usually more stable than furanose form. Okay, so two different crystalline forms of glucose were discovered because there's an alpha and beta sort of glucose, right, when it forms a ring, right. So that means the alpha and beta will have different crystalline forms. So this would indicate that they are different stereoisomers. So alpha glucose has optical rotation of 112.2. So optical rotation, this is something that you would be able to measure in the lab. So the lab practical actually has this sort of measurement. So a solution of beta glucose will have optical rotation of 18.7. So this is 11.2, this is 18.7. So one is a lot higher than the other. Okay, but the interesting thing about sugars is that if you put alpha glucose in the solution, initially when you measure is 112.2. But after a few minutes, right, the solution will slowly equilibrate and you will get a final equilibrium value of 52.5. That means from 112 it will slowly change to 52.5 in the solution. If you dissolve beta glucose from 18.7, it will slowly increase to 52.7. So this actually leads to the concept of anomerization and mutarotation. Okay, so the change in specific rotation is because the alpha and beta carbohydrates will be converted into an equilibrium mixture with both alpha and beta, but of course in different ratios. So there's a certain optimal ratio. So as it switches from alpha and beta to the equilibrium mixture, right, it will cause a change in specific rotation. So this is referred to as mutarotation. So this sort of changing is possible because the cyclic hemiacetals, right, are in equilibrium with the open chain form. So that means the open chain form is present but in quite small quantities. Okay, an anomer, it refers to the alpha and beta hemiacetal. So alpha is an anomer, beta is also a anomer. And the process of changing between alpha and beta, right, it's called anomerization. So when alpha becomes an equilibrium mixture, right, this is called anomerization. And the carbonyl carbon that causes this thing to happen, right, so the carbonyl carbon is also called the anomeric carbon, because the carbonyl carbon is the one that gives the alpha and beta stereocenter. So important thing here is that all these terms here, right, are similar. They are related, but the meaning is quite different. So you need to study this properly, right, and not mix up the terms. So they are related definitely, but there is a small difference in the meaning. So for instance, one good thing to note that is anomerization causes mutarotation. Mutarotation is what we observe, but anomerization is the cause of the mutarotation. Okay, so these are examples of glucose and galactose. So alpha glucose is specific rotation, beta glucose is specific rotation. After equilibrium, it becomes 52.7. So at equilibrium, 36% is alpha, 63.6 is beta. Galactose is a bit different. Alpha is again higher than beta, but after time it becomes 80.2. So the values are different. It becomes 80.2. So values are different from glucose. And another thing about galactose, how it's different from glucose, is that at equilibrium, right, galactose is only 28.2%. This is 71.8. So the percent at equilibrium, right, varies from sugar to sugar. Different sugars will have different percent at equilibrium. And how we calculate this percent at equilibrium? Quite simple actually. Okay, so you know there's a X amount of alpha, X amount of beta, and this is the optical rotation. So this is the after equilibrium. So at equilibrium, there's a certain amount of X, certain amount of Y. So substitute Y with 1 minus X, 1 being like 100%, X is the fraction. So substitute Y with 1 minus X. So 1 minus X this way. So in this, when you substitute this way, right, now you're only left with one unknown, X. So now it's very easy to calculate X. So it's very straightforward to calculate X after you only have one unknown. So this sort of calculation will allow us to know what's the percent at equilibrium. So it's a fairly straightforward calculation. Okay, now we move on to glycosidic bonds. So glycosides are carbohydrates in which the anomeric carbon is bonded to something else. So in many cases, right, anomeric carbon is bonded to another sugar. So this is very, very common. So this is how you form disaccharides and polysaccharides, where the anomeric carbon is bonded to another sugar. So the glycosidic bond is the bond with the anomeric carbon. So it's usually bonded to another sugar, but it can be bonded to basically anything. Like this is glucose bonded to quercetin. This is glucose bonded to quercetin. So this is also a glycosidic bond. This is also a glycosidic bond. So the red here is the anomeric carbon. So the anomeric carbon can be bonded to any carbon. The anomeric carbon, in this case glucose, right, can also be bonded to another anomeric carbon. So basically you need only one anomeric carbon to form a glycosidic bond, but it can also be formed between two anomeric carbons. So minimum 1, maximum 2 for glycosidic bond. Okay, so Glycosidic bonds can be formed by either alpha or beta hemiacetal. So the name quercetin 3 beta glucoside, right, means that the glucose here is in the beta position and is bonded to the third carbon of quercetin. It's in the beta position bonded to third carbon of quercetin. Okay, so notice here that the name is already fixed, is beta, it doesn't change anymore. Okay, this is because when a glycosidic bond is formed, right, the cyclic hemiacetals become cyclic acetal. So you see name change. So when there's a name change, means the properties are different. So acetal and hemiacetal, so the cyclic acetals, they are not in equilibrium with the open chain form. So that means once you form the glycosidic bond, right, glycoside cannot undergo mutual rotation. Glycosides cannot undergo mutual rotation. So once you form an alpha or beta glycosidic bond, right, it is stuck that way. That means it's not interconvertible. So unless you hydrolyze the glycosidic bond into, that means you split the molecule, right, alpha and beta is basically stuck there. It doesn't undergo mutual rotation or anomalization anymore. So a little bit of the terminology. So what's the difference between glucoside and glycoside? And also there's a related term called fructoside. Okay, so gluco and fructo, these are from the sugars glucose and fructose. And glycoside is from the glycosidic bond. So glycoside is a general term. Glucoside is a glycoside of glucose. Fructoside is a glycoside of fructose. So this is in terms of the name. And in terms of biological significance, okay, even with the same sugar, glucose, which is actually the most common sugar, so starch has alpha glucose, alpha, and cellulose has beta glucose, so there will be beta all the way. So they differ only in the glycosidic bond. But you can see starch is digestible, cellulose is not digestible, because the alpha and beta, right, actually changes its shape by quite a lot. The shape of the starch and cellulose molecule is completely different, even though the it's still from glucose. So with that, that's the end of the first lecture. So thank you for listening.